Modern forced air heating relies on mechanical brute force, creating immense energy waste, uncomfortable drafts, and frequent mechanical failure. Yet 2,000 years ago, Roman engineers built a passive thermal machine that operated with zero electricity and absolutely no moving parts. This system, known as the hypocaust, maintained steady temperatures inside colossal bathhouses and military outposts across the freezing frontiers of the Roman Empire. We often assume recent technology is inherently superior, but looking closely at ancient frictionless engineering reveals solutions to the massive energy demands of the modern world. Roman historian Pliny the Elder credited the invention of this thermal technology to a flamboyant first-century real estate developer named Sergius Orata. The archaeological record tells a different story. Excavations in Magna Graecia proved that rudimentary underfloor heating was fully operational in Hellenic settlements more than a century before Orata was born. Orata simply recognized a lucrative opportunity. He refined the Greek design, aggressively marketed it as a luxury amenity for seaside hanging baths, and sold it to wealthy Roman patricians. Rome rarely invented from scratch. Their supremacy lay in taking existing thermodynamic principles, standardize the building materials, and deploy them on a massive imperial scale. The process began outside the primary living space, in a sunken furnace room. Here, enslaved laborers continuously fed wood and biomass into roaring fires. This presents an immediate fundamental physics problem. Without an electric blower, the heavy smoke should have suffocated the fire rather than traveling horizontally beneath the structure. This cross-section illustrates how Roman engineers utilized the stack effect. The temperature difference created a natural buoyancy-driven vacuum, pulling exhaust up vertical chimneys. By varying these flues, architects manipulated flue friction to pull heat evenly across the entire footprint, eliminating cold corners. The entire building functioned as a highly calibrated, continuous thermal machine, powered entirely by gravity and pressure gradients. This 3D cutaway reveals the suspensora, a floating floor supported by a vast grid of uniform ceramic pillars. Atop these base tiles, builders poured opus cinemum. This specialized mortar combined crushed terracotta, brick dust, and volcanic ash to create a completely waterproof seal. This specific mixture of stone and ash possessed immense thermal mass. It absorbed the violent fluctuating heat from the furnace gases below and stored it like a massive geological battery. The floor then steadily radiated infrared energy upward. Instead of blowing hot air into empty space, the hypocaust directly heated the solid objects and human bodies in the room. Following the Roman Empire's collapse, this mathematical approach to thermodynamics was lost to Western Europe, initiating centuries of smoky hearths and freezing stone floors. Yet the exact same thermodynamic principles evolved independently in the frigid climates of the Korean peninsula, where traditional dwellings utilized a passive underfloor heating system known as the ondol. In 1914, American architect Frank Lloyd Wright experienced an ondol firsthand while visiting Japan. This invisible warmth prompted Wright to replace traditional heating with a radiant affair of climate. Wright brought this concept back to the American suburbs, embedding copper hot water pipes directly into the concrete foundation slabs of his affordable Usonian homes. By trading thick smoke for clean, circulating water, Wright effectively resurrected the heavy thermal mass of the Roman hypocaust for mid-century mass housing. Today, the construction industry faces strict new decarbonization mandates, like the BC Energy Step Code. Traditional forced air furnaces leak too much energy to pass these aggressive net zero standards. To comply, modern mechanical engineers rely on this modern radiant floor assembly, returning to the Roman blueprint by embedding continuous tubing directly inside dense concrete subfloors. Pairing this massive thermal inertia with modern air-to-water heat pumps achieves peak thermodynamic efficiency at extremely low operating temperatures. The Roman hypocaust serves as the primary blueprint for a resilient, sustainable future, using an engine with no moving parts to ally with the immutable laws of thermodynamics.